Hello, and welcome to this presentation on the physics of magnetic resonance imaging. My name's Martin Graves and I'm a consultant clinical scientist at Addenbrooke's Hospital. The learning outcomes for this series of 3 lectures on MR physics are shown as in the slide. So after lecture 1, you should be able to explain how nuclear spin gives rise to magnetic resonance and understand the principles of T1, T2 and T2 star relaxation. After lecture 2, you should be able to explain the principles of MR image formation and describe the spin echo and gradient echo pulse sequences. And after lecture 3, you should be able to outline the basic components of an MRI system and also understand the safety issues related to MRI. In the 4th lecture, Professor Ferdiger Gallagher will talk about some clinical and research applications of MRI. Briefly, magnetic resonance imaging is based upon the phenomenon of nuclear magnetic resonance, or NMR. So if we look at the various terms that make up NMR, firstly, MRI primarily looks at the nucleus of hydrogen. A typical adult is approximately 60% water and 16% fat, so it's possible to create images which are sensitive to the protons within water and fat molecules, although other NMR active nuclei can also be imaged in certain circumstances. Now, MRI uses strong magnetic fields, and therefore the protons have a magnetic moment which can interact with the magnetic fields of the MRI system to create images. These hydrogen protons can be considered to precess at a specific frequency, and therefore they can interact with a matching or a resonant external alternating magnetic field, which can be used to manipulate the magnetization. MRI has a wide range of clinical applications. In neurology, it can be used to investigate stroke, multiple sclerosis, and brain tumours. In general oncology, it's used for the diagnosis, staging, and looking at the response of cancers to treatment. In musculoskeletal parts of the body, it can be used to investigate trauma and joint degeneration. In the cardiovascular system, which is the heart and blood vessels, MRI can be used to look at both the morphology or the structure of the heart as well as the function, how well it's contracting. MRI is also widely used for infectious diseases and inflammation, and also looking at congenital or anatomical defects. Here are some example MRI clinical applications. Here we have a whole body MRI scan representing the distribution of the protons in water, and on this side the distribution of the protons in fat. This is a section through the brain, and the arrow is pointing towards an active multiple sclerosis plaque, which appears very bright due to the administration of an MRI contrast agent. Here we have a musculoskeletal example, the knee. Here we have the femur at the top and the tibia at the bottom with the meniscus between them, and the arrow is pointing to a torn meniscus. This is an example of a 3-dimensional magnetic resonance cholangiopancreatography scan, which looks at the bile ducts. So here, for example, you can see clearly the large structure is the gallbladder, and then above here we have the intrahepatic bile ducts. This is a magnetic resonance angiogram, and this represents or shows the blood vessels within the neck here going up into the intracranial circulation. And the contrast mechanism for these images is simply because the protons happen to be moving. This is an example of a cine cardiac MRI scan, so you can actually see the heart beating. So the acquisition takes place over a number of heartbeats. This is in what's known as the short axis view, where the bright signal is the blood. The darker signal around the outside here is the left ventricular myocardium. The darker regions inside the left ventricle are the papillary muscles, and then on this side we have the right ventricle. So the acquisition is synchronized to the patient's ECG, so as the heart contracts, you can clearly see the motion of the myocardium and the thickening of the myocardium. This is an example of a dynamic contrast enhanced four-dimensional magnetic resonance angiogram. This is where we inject a bolus of an MRI contrast agent, and you can see how it passes through the blood vessels in a dynamic fashion. So first of all, we see the enhancement of the pulmonary circulation, and then the arterial circulation, certainly going up here into the carotid arteries, and then we see the venous return here in the jugular veins coming down. This is an example from some of our research work where we've been looking at acquiring very high resolution images of the carotid wall, which is a potential area for rupture of atherosclerotic plaques and for strokes. And you can clearly see on this side that the bright signal pointed to by the arrow represents a very thick fibrous cap around a lipid core, which is part of the atherosclerotic plaque surrounding that vessel. Here's an example of fetal MRI. So this is actually imaging the fetus in utero, and this is obviously a case with twins, and we can see very nicely demonstrated the brains of the two twins here, and also we can clearly see the placenta. This is another example of very high resolution MRI imaging, this time where we've segmented the data to clearly show you the semicircular canals here in the three planes, and also the cochlea. You can see how that's spiraling around. These images are often used for cochlear implant surgical planning. And then finally, this is an example of functional magnetic resonance imaging, where the color overlay on the image there represents the change in blood flow that is associated with the subject actually tapping their fingers, actually activating their motor cortex. So we're all familiar with the fact that the Earth has a magnetic field. That's the reason why compass needles point almost north. And we can measure magnetic field strength in units of either Gauss, after the child prodigy Carl Friedrich Gauss, or more modernly the SI unit being the Tesla, named after Nikola Tesla, the famous Serbian-American inventor. So the Earth's magnetic field is approximately 60 millionths of a Tesla, or 60 microtesla. Another hugely important use of magnets is for sticking plastic letters to the doors of your refrigerator. And these magnets may go up to around 3,000ths of a Tesla, or 3 millitesla, and probably about 50 times stronger than the Earth's magnetic fields. Stronger magnets, like those you might see in a junkyard for moving heavy iron objects around, may be around half a Tesla, or say 10,000 times stronger than the Earth's magnetic field. And in order to generate such large magnetic fields requires the use of an electromagnet, where the magnetic field is created by an electric current flowing through a wire wrapped a large number of times around the iron core. And that helps to increase the magnetic field. Finally, the magnets used in the NHS for MRI are typically either 1.5 Tesla or 3 Tesla. This is a picture of the 3 Tesla MRI scanner that we have in the radiology department in Addenbrooke's. And so this magnet is about 50,000 times stronger than the Earth's magnetic field. The very strong static magnetic field associated with clinical MRI systems pose a serious safety risk with any ferromagnetic object, be it scissors or in this case a wheelchair, turning into a projectile due to the attractive force of the magnet. Fortunately, nobody was injured in this case, but this wheelchair would have been attracted to the magnet at around 30 miles per hour. As has been previously mentioned, MRI is based on the principle of nuclear magnetic resonance that was discovered by Felix Bloch working at Stanford and Edward Purcell working at Harvard almost simultaneously in 1946. They were then subsequently awarded the 1952 Nobel Prize in Physics for their development of new methods for nuclear magnetic precision measurements and discoveries in connection therewith. The initial concept for the medical application of NMR originated with Raymond Damadian in 1971, and he and his colleagues at the State University of New York, who were starved of mainstream research funding, even went so far as to design and build their own superconducting magnet operating in their Brooklyn laboratory, and the first human body NMR image is attributed to them. NMR imaging of two tubes of water was first demonstrated by Paul Lauterbur in 1973. His seminal paper, Image Formation by Induced Local Interactions, Examples Employing Nuclear Magnetic Resonance, which was published in Nature in 1973, was originally rejected. However, 30 years later, Nature placed this work in a book of the 21 most influential scientific papers of the 20th century. In the UK, a lot of work in magnetic resonance imaging and NMR was performed primarily at the universities of Aberdeen and Nottingham, with slice selection, amongst other things, being invented by Professor Sir Peter Mansfield at the University of Nottingham in 1973. The first commercial MRI system was developed by EMI in 1975 in the UK, primarily on the basis of money that they had earned from the Beatles and selling their albums. In 2003, the Nobel Prize for Physiology or Medicine was awarded to Lauterbur and Mansfield jointly for their discoveries concerning magnetic resonance imaging, much to the chagrin of Raymond Damadian, who also felt that he should have been included. The main advantages of MRI include the absence of ionizing radiation, which is used in the X-ray based imaging techniques. MRI only uses magnetic fields for spatial localization. MRI is truly multiplanar. We can acquire images in the axial, coronal and sagittal orientation, as well as single and double oblique orientation, such as here, where we've acquired images in the short cardiac axis. MRI also allows for multiple contrast mechanisms, such as proton density, images weighted towards the T1 relaxation time or the T2 relaxation time, or here, for example, where the contrast in the image is proportional to the diffusion of water molecules, which this high signal here is due to the restricted diffusion in a patient who has suffered an ischemic stroke. We can also look at metabolites within tissues through the use of techniques like MR spectroscopy. MRI also has a very good spatial resolution with a continuously variable field of view depending on the ultimate signal to noise ratio, and also allows for a reasonable temporal resolution in order to obtain dynamic or functional imaging, such as this cardiac cine example. MRI has several limitations compared to other medical imaging techniques. Since it uses very strong static magnetic fields, we have already seen the projectile risk from ferromagnetic objects coming near to the magnet. Magnetic field gradients are also used to spatially encode the MRI signal. The coils that create these gradient fields physically flex like a loudspeaker, creating the characteristic knocking noise during an MRI scan. MRI is also a relatively slow examination compared to X-rays, ultrasound or CT. A typical MRI examination will comprise several imaging series, each producing a different contrast and often in different imaging planes. Whilst we can acquire some MRI images in under a second, most clinical imaging series take several minutes to acquire the data. A complete MRI examination can take anything from around 10 minutes to an hour or even longer, depending upon the complexity of the investigation. Standard MRI sequences cannot visualize cortical bone. Hence, X-ray CT is still the method of choice for trauma imaging due to its speed and its ability to visualize cortical bone. The wide range of imaging parameters makes MRI a complex and expensive technology that requires skilled operators, or radiographers as they're known, to perform the examination. In addition, most MRI scanners are based on superconducting magnet technology, which has a 60 or 70 centimeter patient aperture. However, this can still make some patients feel claustrophobic. Let us now get into a little bit more detailed discussion of how MRI works. For the purposes of this discussion, we will take a fanciful and relativistically inadequate representation of the proton as a spinning ball of charge. Due to the combination of charge and spin, we can consider that the proton behaves as a tiny bar magnet and has a nuclear magnetic moment, mu. The ratio of the magnetic moment mu to the angular momentum J is called the gyromagnetic ratio, or gamma. When placed in a static magnetic field, which we'll call B0, we can consider that mu makes an angle with respect to the direction of B0. It therefore experiences a torque and precesses about B0 at a characteristic frequency, which is omega equals minus gamma times B0. The minus sign, which will get quietly dropped in the future, just means that omega naught defines a clockwise rotation around B0. The proton's precession is analogous to the precession of a gyroscope in the Earth's gravitational field, where r is the distance from the pivot, m is the mass, g is the acceleration due to gravity, and L is the angular momentum. As we have seen in the previous slide, the precessional frequency is dependent upon the strength of the magnetic field. And in our 3 Tesla MRI, protons, which have a gyromagnetic ratio of 42.57 MHz per Tesla, will precess at a frequency of 128 MHz. This is in the radio frequency part of the electromagnetic spectrum and is therefore a much lower frequency than those associated with X-rays. Hence why MRI is considered a non-ionizing imaging modality. Outside of the strong static magnetic field, the protons can be considered to be randomly orientated. Although once placed in the static magnetic field, in addition to the individual protons precessing around the direction of the main field, the protons end up being distributed into one of 2 states, either parallel to B0 or antiparallel. The probability distribution means that just over half of the protons end up pointing in the same direction as the magnetic field. Since the net magnetization is pointing in the same direction as B0, it is effectively undetectable and therefore needs to be perturbed so it is aligned orthogonal to B0. If we denote the Z direction as the direction of the net magnetization at equilibrium, we can perturb the net magnetization M, the red arrow in the diagram, away from Z by applying a second, weaker magnetic field called B1 at right angles to B0. B1 is represented by the yellow arrow in the diagram. If the B1 field is alternating at the same frequency as the natural precessional frequency of the protons, that is to say it's resonant with omega 0, then in the laboratory frame of reference the net magnetization will spiral down for as long as B1 is applied. The simplest arrangement is to apply an alternating voltage to a solenoid, thereby creating an alternating magnetic field inside the solenoid at right angles to B0. In this example, B0 is 3T, or 3 Tesla, so the alternating magnetic field is at 128 megahertz. Once the net magnetization M has been tipped through 90 degrees, if we turn off B1, then M will continue to precess in the transverse plane and, according to Faraday's law, this precession will induce an EMF in the same solenoid that was originally used to create the B1 field. Due to small variations in the uniformity of the B0 static magnetic field, the net transverse magnetization, represented by the cyan arrow in the diagram, will decay in amplitude whilst precessing, and the induced EMF can be seen on the oscilloscope as an exponentially decaying sinusoid. This is known as a free induction decay and is the most basic NMR or MRI signal. The time constant of this decay is characterized by a value known as T2 star. The small positive and negative variations in B0 mean that some nuclei precess slightly faster, the yellow ones, and some precess slightly slower, the white ones, than the nominal omega naught frequency. So the net transverse magnetization decreases in amplitude as the nuclei dephase with respect to each other in the transverse plane. Note that the diagram represents the situation in the laboratory frame of reference. So far, we have provided a very brief overview to the principles of NMR relevant to MRI. We shall now revisit these concepts in a little more detail before looking at how nuclei return to equilibrium via the processes of relaxation. We will address how images are formed in the next lecture. The physical basis of nuclear magnetic resonance centers around the concept of a nuclear spin, its associated angular momentum, and its magnetic moment. Spin is a purely quantum mechanical quantity with no easy classical analogy, despite the simplified representation used here. For a hydrogen nucleus, that is to say a single proton, the spin angular momentum J and the magnetic moment mu are related through the proportionality constant gamma, known as the gyromagnetic ratio, which is a fundamental constant of a nucleus. The magnitude and direction of the spin angular momentum J is characterized by the nuclear spin quantum number I. Nuclei with an equal number of protons and neutrons have zero spin. If the number of neutrons plus the number of protons is odd, then a nucleus has a half integer spin, and if the number of neutrons and the number of protons are both odd, the nucleus has integer spin. The vast majority of clinical MRI involves the use of hydrogen nuclei in water and sometimes fat. Since the nucleus of hydrogen is a single proton, it has a spin quantum number of 1/2. In 1896, Peter Zeeman observed the splitting of optical spectral lines in an external magnetic field. Since then, the splitting of energy levels proportional to an external magnetic field has been called the Zeeman effect, with the effect in the nucleus known as the nuclear Zeeman effect. For protons with a spin quantum number of 1/2, there are two orientations with the magnetic moment quantum numbers of plus and minus 1/2. It's left as an exercise for the viewer to calculate the angle theta. Note that h bar is the reduced Planck's constant equal to h divided by 2 pi. We have already introduced the analogy of nuclear spin to that of a gyroscope, where gravity will cause the gyroscope to experience a torque and therefore precess about the vertical. Here I simply derived the precessional frequency for a gyroscope of mass m, distance r, angular momentum L, and g being the standard acceleration due to gravity. Similarly to the gyroscope, the static magnetic field will cause our spinning nuclei to experience a torque and hence precess around the direction of B0. This precessional frequency is given by the Larmor equation, omega 0 equals gamma times B0. Larmor worked in an era when the basic structure of the atom was still being discovered and quantum mechanics had yet to be developed. His famous equation of 1897 was unrelated to NMR, as this phenomenon was still several decades away from being discovered. Instead, it arose from attempts to explain the Zeeman splitting observed 1 year previously. Larmor's theory was that Zeeman spectral lines were produced by charged particles moving in elliptical orbits. Larmor demonstrated mathematically that these particles should precess around the direction of the applied magnetic field. He further calculated that the frequency of precession was directly proportional to the strength of the applied field times a constant. Larmor's constant was directly related to the particle's charge to mass ratio. In later years, as more became known about atomic structure, Larmor's equation was found to apply to any particle with spin or angular momentum, taking the form we recognise today. The Larmor frequency is a signed quantity and is negative for nuclei with a positive gyromagnetic ratio. This means that for such spins, the precession frequency is negative as shown in the animation. Note that conventionally the Larmor equation is written as omega 0 equals gamma times B0, where omega 0 is the angular frequency of the proton's precession, which is 2.7 times 10 to the 8 radians per second per Tesla. However, this is a number is rather unmemorable, and as angular frequencies are not as intuitively understandable as regular scalar frequencies, I prefer to refer to gamma as 42 megahertz per Tesla, that is to say gamma over 2 pi. Here is a table of some common NMR active nuclei, together with their gyromagnetic ratios. Note that the neutron has spin 1/2 but no net charge. This can be reconciled with the classical model if the neutron is considered as a proton orbited by a negatively charged pion. The neutron is composed of 3 quarks, and the magnetic moments of these elementary particles combine to give the neutron its magnetic moment. We have already seen how the hydrogen nuclei become polarized in a static magnetic field into 2 energy states, and the overall net magnetization is aligned in the same direction as B0. From a quantum mechanical perspective, the energy difference between the 2 orientations in a static magnetic field of B0 is given by delta E equals h bar times the gyromagnetic ratio times the static magnetic field strength, and as such is exactly equivalent to the classical Larmor equation. The population distribution known as the polarization P of the nuclei between the 2 states is characterized by the Boltzmann distribution, which describes the distribution of energy among classical or distinguishable particles, where Kb is Boltzmann's constant and T is the absolute temperature. The human body temperature is normally around 310 Kelvin. If we inject energy into the system at an angular frequency of omega 0, we can induce transitions between the 2 energy states. A spin-up nucleus can absorb energy and transition to a spin-down state, and a spin-down nucleus can give up energy and transition to spin-up. This excitation must be at the specific frequency to resonate with the nuclei as described previously. The cartoon of Schrödinger's cat is to remind us that the spin and magnetic moment exist in all directions simultaneously, but their average behavior is non-zero in only one of the directions. Therefore, these diagrams are an attempt to provide some additional insights into how NMR works, but their limitations should be appreciated. And if we look at the Boltzmann distribution, then to a first order approximation, we can calculate the polarization as shown above, and as we see at 310 Kelvin and 3 Tesla, that we're getting about 0.001% polarization, which gives rise to our net magnetization. So we can also think about the individual spins, because they have no phase relationship with each other, and there's a very large number of them. We can just think of them as being distributed here on a cone. So we have the larger number in the low energy state here, the smaller number in the high energy state down here. So there's a component of the spins in the Z direction, which we'll call mu Z. And of course, if we subtract the high energy spins from the low energy spins, then we're just left with that small excess in the low energy state. Again, we have those components in Z, but we have a uniform distribution of magnetization in the transverse plane. So essentially what happens is that because they're uniformly distributed, they cancel each other out, so we end up effectively with zero net magnetization. So we lose the individual transverse components, and then all of the Z components we can just pull together, and this gives us our large net magnetization. And this equation gives us an approximate idea of how big that magnetization is. There's a number of fundamental constants in there that you can look up if you particularly wish to do that calculation yourself. But assuming that water contains something like 6.67 times 10 to the 22 protons in a single mil, and at body temperature we find that we get a equilibrium magnetization of about 0.02 microtesla per mil. And if we assume the human head has a volume of about 1.5 litres and is approximately 80% water, we get a net magnetization of approximately 20 microtesla. So the signal that we're getting from the patient is really quite small, certainly in comparison to the static magnetic field that is giving us that net magnetization. So this slide summarizes the process required to create the NMR signal. We firstly need to excite the spins by tipping the net magnetization from along the Z direction into the transverse plane. This is done by applying a short duration pulse of a voltage alternating at the Larmor frequency to a transmit coil, and that creates a uniform magnetic field B1, which is orthogonal to B0 inside the coil. The B1 field rotates the net magnetization into the transverse plane. The precessing and decaying transverse magnetization induces a voltage into the receiver coil, and after we've turned off the B1 pulse, the magnetization will return to thermal equilibrium by these processes known as relaxation. The Bloch equation shown here describes the evolution of magnetization in a large static magnetic field considering spin relaxation and molecular self-diffusion, although we will not consider molecular self-diffusion any further in this lecture. Bloch used the fact that an external field produces a torque on the net magnetization, resulting in its precession at the Larmor frequency. He also reasoned that the decay of the NMR induction signal was due to the individual spins that comprise the net magnetization interacting with each other and their environment, a process Bloch termed relaxation. Bloch introduced two relaxation times, one to account for the recovery of the longitudinal magnetization back to equilibrium, or M0, known as T1, and one to account for the decay of the transverse magnetization, known as T2. He also assumed that the decay of the transverse magnetization and recovery of the longitudinal magnetization was exponential. T1 and T2 were defined phenomenologically and not from fundamental principles, although Bloch did correctly conclude that T1 must result from thermal motion and T2 from intra and internuclear actions. Note that in contrast to longitudinal decay, transverse decay conserves energy. The animation shows the net magnetization being tipped into the transverse plane here, followed by dephasing of that transverse magnetization and recovery of the longitudinal magnetization. Note that the longitudinal recovery is much longer than the transverse decay. If we temporarily ignore relaxation, the left-hand side of the slide demonstrates the block equation for free precession about the static magnetic field along Z. By defining M as a three-dimensional vector and expressing the cross product as the formal determinant, and then using Sarris's rule, we can express the three components of magnetization. On the right-hand side, if we now introduce an RF pulse, that is to say an additional oscillating magnetic field B1 that rotates in the transverse plane at a frequency of omega, and we now make BZ explicitly to be B0, we then have the differential equations for motion in the presence of an applied B1 field. If we include the terms for relaxation, then these three equations are generally referred to as the block equations in the laboratory or fixed frame of reference. Note that the change in the Z component of the magnetization is unaffected by the Z component of the static field. This means that BZ has no effect on T1 relaxation. Similarly, we can see that all three components of the static field affect the transverse or T2 relaxation. It is conceptually much easier to work in the rotating frame of reference. This is like trying to read the label of a 7-inch vinyl record on a turntable that is rotating at 45 RPM. However, if the turntable were large enough, you could stand on it so that you were also rotating at 45 RPM, and then it would be much easier to read the label. On this and the next two slides, we go through the derivation of the equations of motion for the components of M in the rotating frame. If we consider two coordinate systems, mx, my and mz, together with mx prime, my prime and mz primed, the two sets of axes are rotated relative to one another where the origins of the two sets coincide. If we also introduce two sets of unit vectors with the same unprimed and primed axes, we can express the magnetization vector M in terms of the components along either set of axes. Since the origins coincide, a point is represented by the same vector M in both systems. Only the components of M are different along the different axes. So the time derivative of M in the laboratory frame is given by equation 1, and in the rotating frame by equation 2. Since the left-hand sides of equation 1 and 2 are identical, we can obtain the following relationship following regrouping of the terms. To interpret the time derivative of the rotating unit vectors, think of them as a position vector. This then shows the fundamental relationship between time derivatives for a coordinate system rotating at an angular velocity of omega. With a little more rearranging and substituting, we obtain equation 3, whereby it is apparent that the magnetization rotates about an effective magnetic field, shown here, in the rotating frame, just as it rotates about the applied magnetic field in the laboratory frame. If the frequency of the rotating frame equals the frequency of precession, then the magnetization is static in the rotating frame. If we now introduce an RF pulse to create a rotating field along the x-axis, then that adds to the effective field, and we can see that if omega equals the Larmor frequency, then B1 is static and the net magnetization rotates about the x-axis at a rate equal to gamma times B1. Using the left-hand rule, with your thumb pointing along the x-axis, you can see that the rotation is clockwise about B1. By changing the phase of B1, it's possible to get the magnetization to rotate about any desired axis. Note that if omega does not equal the Larmor frequency, then the magnetization will precess around the effective magnetic field and not into the transverse plane. Therefore, significant signal is only obtained when the frequency of the stimulus is the same or nearly the same as the natural vibration frequency of the MR system, i.e. we have a resonant condition. So this classical mechanics approach is in agreement with our quantum mechanical view of resonance. This slide shows the comparison of the motion in the laboratory frame and a frame rotating at the Larmor frequency. In the laboratory frame, we can see the B1 field rotating at the Larmor frequency, and therefore the net magnetization spirals down into the transverse plane. In the rotating frame of reference, which is rotating at the Larmor frequency, then the B1 field appears stationary and the net magnetization simply rotates about the axis of the applied B1 field, in this case along the X prime axis in the rotating frame. The magnetization will tip at an angular frequency given by gamma times B1, and depending on the time that we play out this pulse of RF for, TRF, that will dictate the flip angle alpha degrees. In this case, we've flipped the spins through pi over 2 or 90 degrees. Therefore, a pulse of that duration and that amplitude will be called a 90-degree pulse. Of course, we may flip it by less than 90 degrees, in which case our transverse magnetization is going to be given by the sine of the flip angle. If we now look at the solution to the Bloch equations with relaxation in the laboratory frame, if we just slightly simplify the equations as here, the solution for the case where B is equal to B naught, the X, Y and Z magnetization is shown here as a function of time, with the transverse components decaying due to T2 and the longitudinal component recovering due to T1. Of course, the equilibrium solutions where T is infinite is that we have zero transverse magnetization and the longitudinal magnetization has reached back to equilibrium, to the M0 value. Of course, it's much easier to deal with this in the rotating frame of reference, where we are rotating at the Larmor frequency, and if we express the magnetization in complex form, then these equations simplify to these two differential equations, which have the following two solutions. So again, we simply see that the rotating transverse magnetization decays with e to the minus t over t2, and the recovering Z magnetization recovers with 1 minus e to the minus t over t1. Here we can see the relaxation in the laboratory frame as the yellow arrow spirals back up to equilibrium. Sometimes this is called the witch's hat. But we can also look in the rotating frame of reference, whereby we see the green transverse component decaying due to T2 relaxation, and we see the red longitudinal component recovering due to T1 recovery. Again, here we can see the curve in the rotating frame of reference there, recovering 1 minus e to the minus t over t1. So if we look at the rotating frame of reference, we can see in this example here the T2 decay, and the T2 is the characteristic time constant when the magnetization has decayed by 63%, or there's 37% remaining, whereas for the T1 recovery, the time constant is when we have recovery of 63% of the magnetization. Of course, the magnetization will eventually recover back to the equilibrium value. Again, this is an example from biological tissue. We can see that the T2 relaxation time is about an order of magnitude shorter than the T1 relaxation time. Just a little bit more about RF excitations. So we know that an RF pulse is an alternating magnetic field of amplitude B1, either in microtesla or Gauss, applied for a time TRF at the Larmor frequency, and in that case it will tip the net magnetization by this particular flip angle given by omega-1t, which is equal to gamma B1 times the duration of the RF pulse. So here's an example of a hard RF pulse, just a pulse that is turned on and off for a short period of time. So in this case we have a rectangular or hard RF pulse of 1 millisecond duration, and if we have a B1 of 5.87 microtesla, then that will tip the magnetization by 90 degrees. Note of course that B1 is considerably smaller than the B0 fields we've been talking about. So RF pulses are the only effective way to rotate magnetization, and different flip angles get used for different applications. In practice, RF pulses will be shaped. So more generally, the flip angle is going to be equal to the time integral of the B1 pulse. For example, here we have what is called a soft RF pulse. This will be a pulse which will be suitable for exciting a thin slice of spins within the body. We'll talk a bit more about that later. And it's important to remember that MRI uses the alternating magnetic fields in the RF part of the electromagnetic spectrum. It does not use radio waves, as is sometimes mentioned in the popular literature. Here we can look at essentially the quantum approach to excitation, whereby we can consider that the RF pulse, with its frequency equal to gamma times B0, creates a photon of energy equal to omega naught times the reduced Planck's constant, and that will have the effect of promoting a spin from the low energy or spin up state to the high energy spin down state. And we can essentially think of a 90-degree pulse as receiving sufficient numbers of these protons so that we can equalize the populations in the high energy and low energy states. Following the RF excitation pulse, the transverse magnetization will continue to precess in the transverse plane, but the individual spins that make up the net magnetization will start to dephase with respect to each other. So this is due to potentially small variations in the uniformity of the static magnetic field of the scanner itself, as well as non-uniformities that arise from actually putting a patient inside the scanner. So here we have in the laboratory frame of reference, we can see that the net magnetization, the turquoise arrow, is diminishing in amplitude, is decaying away due to the dephasing of the constituent spins. And here, because we're in the laboratory frame of reference, I've shown the spins that are going slightly faster than the average in yellow, while those processing slightly slower in white, so we can see that eventually we get a complete dephasing of the magnetization. So this free induction decay signal that we acquire has an envelope which is given by the time constant T2 star. It's called T2 star and not T2 because we have the additional effects of these unwanted field non-uniformities. So it's actually the relaxivities 1 over the relaxation times that add. So here's our proper tissue T2 value, but then here we have the component T2 prime, which is due to the additional effects of the field non-uniformity and the effect of the patient. And sometimes we can look at this 1 over T2 prime effect as being equal to gamma times this small variation in the uniformity of the static magnetic field. So by combining 1 over T2 plus 1 over T2 prime, we get the 1 over T2 star decay that we have for a free induction decay envelope. The most basic pulse sequence used in MRI is the spin echo. And the spin echo involves two RF pulses. We're not going to consider the spatial localization gradients at the moment, but we have a 90-degree excitation pulse, which at a time tau later, we have a 180-degree refocusing pulse. And this means that at another time tau later, the magnetization will refocus, producing an echo. So the time from the 90-degree pulse to the center of the echo is known as the echo time, or TE. Now we need to repeat this spin echo process a number of times. Certainly when we start performing imaging, we need to perform it a number of times in order to build up our image. And the time from applying one 90-degree pulse to a subsequent 90-degree pulse is known as the repeat time, or the repetition time, TR. The advantage of the spin echo sequence is that it can eliminate this T2 prime dephasing, and it does that through the use of this 180-degree refocusing pulse. So if you look at the animation, here we have our 90-degree excitation. The magnetization starts to dephase in the transverse plane. Then we apply the 180-degree pulse, and then all the magnetization that was previously dephasing, because of this phase flip, will now naturally rephase. So dephasing, we flip the magnetization. Now we have natural rephasing and the formation of an echo signal. So immediately following the 90-degree pulse, we have the dephasing with our T2 star envelope. And then once it's been flipped by the 180, the nuclei will start to come back into phase coherence, again forming this signal which is known as an echo at the echo time. Clearly we've got some loss in amplitude, but that's due to T2 decay, and that is irreversible over the time scale of this experiment, whereas the static field non-uniformities that give rise to T2 prime have not changed over the time scale of this experiment. So therefore the amount of dephasing is matched by the identical amount of rephasing if we have the 180 symmetrically placed between the 90 and the echo. So effectively what we're doing is eliminating that 1 over T2 prime component, or saying that we have got rid of this small variation in the static magnetic field. And then we have our true T2 decay envelope here. Clearly T2 is going to be longer than T2 star. And in this particular case, we can see that for this curve, the T2 relaxation time characteristic of the curve is 27 milliseconds. So that's the time for the magnetization to decay from its maximum value down to 37%. So what actually causes this T2 relaxation? Well, we can think that the magnetic moment of neighboring protons behaving like little tiny bar magnets will alter the local magnetic field, causing this loss of phase coherence. So this is why we talk about T2 having spin-spin relaxation. And essentially the T2 relaxation time decreases as you find tissues that actually tumble slower and slower. So if we have a water sample, for example, up here, where the molecular tumbling rate, the protons are tumbling very rapidly, then we will find we'll have quite a long T2 relaxation time, essentially because of motional averaging. Whereas as the tumbling rate decreases, and that may be due to proximity of the water molecules to other macromolecules, as we'll discuss later, we can see that the T2 relaxation time starts to get shorter and shorter. And again, it's essentially down to the rate of tumbling of the individual molecules. Although it's not performed very widely clinically, we can actually calculate or measure this T2 relaxation time on a pixel by pixel basis, and we can simply do this by acquiring images with different TEs. So therefore we will end up with different points on the transverse decay curve, and then we can fit this model of the decay to those data points, and from that we can estimate the relative proton density, M0 here, as well as the T2 relaxation time. Of course, we need to ensure that we have a very long repetition time in order to make sure that the magnetization is fully back to equilibrium before we perform our next excitation, but this time with a different echo time. So it can be quite time consuming to make T2 relaxation measurements. So we've already discussed how T2 relaxation occurs. And remember that T2 relaxation conserves energy, so there's no energy loss associated with T2 relaxation. Whereas with T1 relaxation, there is energy transfer. And T1 relaxation arises because we need to generate an alternating magnetic field at the Larmor frequency. Clearly, we've turned off the external RF pulse. So where do we get this alternating magnetic field? Well, this comes from the fact that as molecules tumble or vibrate, the protons are exposed to an alternating magnetic field, and that can then stimulate relaxation. So T1 relaxation is dependent upon the molecular motion and the tumbling rate, very similar as we discussed with T2 relaxation. So for example, here it could be due to intramolecular dipole-dipole interactions. Here's a tumbling water molecule. Here's one proton in the center here, and you can see as the water molecule tumbles, the other proton is experiencing a difference in magnetic field due to the magnetic field of the first proton. So this sees an alternating intramolecular dipole-dipole field, and this alternating magnetic field, if it's the same or matches the Larmor frequency, then that can induce this or stimulate this relaxation properties. Similarly, if we have intermolecular dipole-dipoles between two protons or between a proton and electron, as we've got here, again, depending on that tumbling rate, we will be generating alternating magnetic fields of different frequencies, and those frequencies that happen to match the Larmor frequency will stimulate the relaxation. So in terms of the molecular tumbling rate, again, here where we've got very rapid tumbling, such as just in a sample of water, then we have a long T1, but as the molecules tumble slower, we may get down to somewhere here, for example, a fat molecule, which is quite large. The protons therefore tumble much slower, and therefore they tumble nearer the Larmor frequency. So therefore we have much more efficient T1 relaxation in fat. So fat tends to have the shortest T1 of the tissues in the body. However, if the molecular tumbling starts to go slower, then we find that the T1 relaxation time then increases again, because we're not matching the relaxation to this sweet spot here. From a quantum mechanical approach, we can again think that this quantum energy that comes from these inter or intramolecular tumbling effects can actually stimulate a move from the high energy to the low energy state, and the energy that is then given off in that process gets absorbed by the surrounding lattice, which is other protons in other macromolecules that are in the vicinity of the water molecules. So this is where we then lose the energy as part of the T1 relaxation. So the T1 relaxation is really given by this molecular tumbling rate. So we can see in this cartoon that we have free protons here, which are not bound towards any macromolecules. And we can see that on this diagram, which essentially represents the number of spins against their tumbling rate, that there is a wide distribution of tumbling rates within these free protons. And so therefore we find that those that just happen to tumble at the Larmor frequency and create the appropriate alternating magnetic field to stimulate that relaxation is quite small. So therefore T1 relaxation is quite inefficient, and the T1 relaxation time can be quite long. So if we just had a glass of water, the protons in that glass of water will be tumbling at that wide range of frequencies, and therefore the T1 relaxation time will be relatively long. Whereas if we look at the protons which are bound to macromolecules here, they tumble very slowly. Again, we have this kind of distribution with probably only a very tiny number that happen to be tumbling at the Larmor frequency. So again, we will find that for protons that are bound to macromolecules, the T1 relaxation is again very inefficient, and the T1 relaxation time is quite long. Whereas in this sort of ideal situation here, where we've got protons which are sort of restricted in their tumbling rate due to their proximity to the macromolecule, they have a range of tumbling frequencies, but there are generally more of them that will be tumbling at just the right Larmor frequency for the field strength, and therefore the T1 relaxation is more efficient and the T1 relaxation time is shorter. As we said before, that essentially goes for fat as well, with this a very large molecule with all of these protons. So again, the fat molecule tumbles relatively slowly, and more of the molecules tumble at near the Larmor frequency. So therefore the T1 relaxation is more efficient, and therefore fat has the shortest T1 of any of the tissues in the body. So again, similarly to T2, we can also try to measure T1 relaxation, and the simplest method for this would be to acquire images at different repetition times, but whilst keeping the echo time as short as possible to minimize T2 decay. So again, if we repeat the experiment multiple times, and this time we change the repetition time, then we can acquire points on the recovery curve, and then we can fit the T1 recovery equation to those points, and again derive a relative proton density as well as the T1 relaxation time. And again, having to do these multiple experiments at multiple different repetition times means that the whole process to measure T1 relaxation is quite time consuming, although there are more advanced pulse sequences now that can do it much more rapidly. So although we are yet to discuss the mechanism for creating images, I think it'll be quite useful just to have a look at what the effect of these timing parameters are on a spin echo image. So if we have a very short repetition time, then we will not get full recovery of the magnetization. And if we've got different tissues with different T1 relaxation times, then we'll be able to derive a difference in the signals, i.e. a contrast, which is dependent upon the T1 relaxation time. And if we are looking for a T1 weighted image, then we ideally want our echo time to be as short as possible to minimize any T2 decay. So a TR of approximately 500 milliseconds with a TE of about 10 milliseconds will give us what we clinically call a T1 weighted image, where the contrast in the image is in proportion to the differences in the T1s of the tissues. So as we just illustrated, fat around the surface of the skull here looks very bright because fat has a very short T1. Inside the ventricles, the dark structures here, that is the cerebrospinal fluid, and that has a very long T1. So in that case, it appears quite dark. If we increase the repetition time down here, then we are reducing the T1 contrast, and we're starting to be in a position whereby the magnetization has recovered back to equilibrium. Essentially, the signal differences now represent the proton densities of different tissues. And again, because we've got a short echo time here, there is minimal T2 decay, so therefore we end up with an image which is proton density weighted. So again, we can see here that the white matter has a slightly lower proton density than the grey matter, so the white matter is slightly darker in this image. If we move this way, we are now increasing the echo time. So now here we have a long TR and a long TE relatively. So this may be a TE now of 200 milliseconds with a TR of about 4,000 milliseconds. And so that means now that we are somewhat down the T2 decay curve. And again, if we've got different tissues with different T2 relaxation times, then that will give rise to the contrast that we see in the image. So here in particular, we can see that the fluid, the cerebrospinal fluid, because that has a very long T2 relaxation time, it appears very bright in the image. So there's a little bit of an overview of image weighting. We're just going into a little bit more detail then about how we do achieve these different image contrasts. So here are some typical T1 and T2 relaxation times. There are approximate values. There's quite a wide range of overlap in normal tissue. Well, we can see generally that the T1 relaxation time is about an order of magnitude shorter than the T2 relaxation time, except where we get down to things like very watery tissues down here in the CSF. So here I've just taken those values and plotted some T1 recovery curves. Green is CSF, red is grey matter, and blue is white matter. So these are the T1 recovery curves. So these essentially represent the recovery of the Z magnetization. And similarly, I've plotted without the dotted lines the T2 decay curves for CSF and for grey and white matter. Again, it's very difficult to see on this scale the differences between the grey and white matter, which as you can see is really quite small. So if we have a long enough repetition time, then the magnetization will start to return, and the differences here will be due to the relative proton densities. If we have a very short repetition time, then you can see that the differences between the blue, the red dotted line and the green line start to increase and then start to fall off again. So if we wanted to perform a T1 weighted scan, we'd probably be operating with a TR round about the sort of 500, 600 millisecond region. As I say, it's very hard to see on this graph the effect of the T2, but again, if we're really primarily looking to see increases in fluid on T2 weighted imaging, lots of pathologies increase the T2 relaxation time. So again, somewhere around about the 100 millisecond part will give you very good contrast between the signal from the CSF and much lower signal between the grey and white matter. So if we just look in more detail, for a T1 weighted image, we've just reduced the time scale here. So you can see here are the T1 relaxation curves for white matter, grey matter and CSF. Of course, we can only detect the magnetization in the transverse plane. So although this is recovery in the Z direction, we then need to perform our spin echo experiment to tip the magnetization into the transverse plane, and then we will start to see T2 decay as well. But we can see approximately now that the signal is going to be on the basis of this equation. We're going to have recovery based on T1 and decay based on T2. So we want to keep TE as short as possible, and we want to keep TR as short as possible to ensure that we have this good differentiation between these three tissues. And again, approximately with this image, we can see that the white matter here in the center of the brain is brighter than the grey matter, which is around the edges here, slightly darker shade of grey, compared to the CSF, which is really quite dark here in the ventricles. In this case, we've gone for a minimum echo time, just for illustrative purposes, of about 20 milliseconds and a TR of about 500 milliseconds. Similarly now for T2 weighted imaging, I've reduced the time scale along here to clearly show the T2 decay over 1000 milliseconds, and then I've changed the scale here so you can clearly see the recovery of the magnetization up to 10 seconds, getting back to equilibrium. So in T2 weighted imaging, we want effectively a very long TR, as long as we can make it. Of course, that will affect our overall scan time, but that means that the longitudinal magnetization will hopefully have recovered back to its equilibrium value before we do the next excitation pulse. But now we've arranged for a longer echo time by increasing the time period between the 90 and the 180 degree pulse. So again, you can see here that now we're going to have CSF as being the brightest signal, and again slightly higher signal from grey matter compared to white matter, but very small difference there. And again, if we look at our T2 weighted image, exactly as predicted, we can see very high signal in the CSF, in the ventricles and surrounding the brain here, but there's very poor contrast between the grey and white matter. But as I say, a number of pathologies will increase the T2 relaxation time, so we will see them as hyper intense, brighter on T2 weighted imaging. And here is an example for proton density weighted imaging, whereby we again have a very long TR, so that all of the magnetization will have recovered due to T1 relaxation, and therefore we are left with signal differences which represents the relative proton densities of the tissues, and we have a very short echo time to minimize the T2 decay that may occur. So again, in a proton density weighted image, we should find that the CSF has the brightest signal, and there should be slightly brighter signal now from grey matter compared to white matter. And if we look at a typical proton density weighted image, again, we can see higher signal within the, or higher signal within the CSF, and we also find that the grey matter on the outside here appears brighter than the white matter, which you can see here in the slightly darker shade of grey. So this is the proton density weighting with a long TR and a short TE. So we'll finish this first lecture with the comparison of a T1 weighted and a T2 weighted image at matched locations in a patient with a brain tumour. So the T1 weighted image doesn't demonstrate much image contrast, although we can clearly see an asymmetry between the left and right hand sides of the brain with something strange going on here. However, on the T2 weighted image, we can clearly see lots of changes in the signal intensity, lots of hyper intense regions on this side of the brain compared to the normal side of the brain. So just illustrating the fact that some of the fluid accumulation associated with this tumour has increased the signal intensity. So therefore this is a more pathologically sensitive sequence, whereas the T1 sequence is probably more anatomically sensitive. Okay, well, thank you for that. We'll be back with the next lecture where we will discuss the mechanism for spatial localization. Thank you. So this is the end of the first lecture, and hopefully you now feel that you could explain how nuclear spin gives rise to magnetic resonance, and also understand the principles of T1, T2 and T2 star relaxation. So thank you very much, and I look forward to talking to you in the second lecture.